From what we have done so far, we know how to evaluate limits of indeterminate form 0 over 0 or infinity over infinity. So for these two types, our technique is to use L'Hopital's rule. So for today, we will introduce other indeterminate forms that may arise from different expressions. So for instance, we will consider limits of the form infinity minus infinity, or we will also encounter limits of the form 0 times infinity. And then later on, we will see that from the indeterminate form 0 times infinity, this will give rise to the other exponential types of indeterminate forms. So, namely, 0 raised to 0, infinity raised to 0, or 1 raised to infinity. So now, our question is, how do we evaluate the limits of the other 5 indeterminate forms? For this, our general strategy is from these 5 indeterminate forms, we will try to manipulate these expressions in order to be of the form 0 over 0 or infinity over infinity. And when we have already done that, we will now be able to utilize L'Hopital's rule. So that is our general strategy for today. So for the other indeterminate forms, we will try to express it in either of these two forms and then apply L'Hopital's rule. So to illustrate our technique, let us consider the following examples. So first, let's have example 1. So here, we want to evaluate the limit as x goes from the right of 0 of 1 over x minus 1 over sine x. So first, we check the form. So checking the form, we have for the first term, we get the limit as x goes from the right of 0 of 1 over x. So this is 1 over 0 plus or positive infinity. And then for the other term, we have the limit as x goes from the right of 0 of 1 over sine x. So this is 1 over sine of 0 plus. So ang problema na lang natin ngayon ay again, sine 0 is 0. So, ito ba ay plus, 0 plus, or 0 minus? So, to identify, let us recall the graph of y equals sine x. So, this is y equals sine x. Here, as x goes from the right of 0, the graph of y equals sine x goes from positive values. So sine of 0 plus is actually 0 plus. No? So we have 1 over 0 plus or positive infinity. So from these two calculations, this tells us that our limit is of the form positive infinity minus positive infinity, or simply put, this is infinity minus infinity. So here we encounter the first of the 5 other indeterminate forms. For this specific form, our general strategy is to simplify the expression and hope that it will yield a limit of type 0 over 0 or infinity over infinity. So when we combine these two terms, we get the limit as x goes from the right of 0. So for the denominator, we have x times sine x. And then for the first term, kulang na ang sine x. So we have sine x. And then for the second term, kulang naman ng x. So now, let us check the form of this limit. So we have the limit as x goes to 0 plus, of sine x minus x. So this is nothing but sine 0 minus 0, or 0 minus 0, so we get 0. And then for the denominator, we have the limit as x goes to 0 plus of x sine x. So we have 0 times sine 0. So again, obviously this is 0. So from these two calculations, what can we say? So this tells us that our limit is indeterminate of type 0 over 0. So this calls for L'Hopital's rule. So using L'Hopital's rule, again, recall that for L'Hopital's rule, this limit after L'Hopital's rule is nothing but the limit as x goes to 0 plus of the derivative of the numerator, so the derivative of sine x minus x, divided by the derivative of the denominator, which is x sine x. So differentiating, we have for the numerator, we have the limit as x goes to 0 plus of the derivative of sine x is cosine x, and the derivative of minus x is minus 1. And for the denominator, we have the product x times sine x. So in order to differentiate this, we will use the product rule. So we have the derivative of x times sine x, or we have 1 times sine x plus x times the derivative of sine x, which is cosine x. So simplifying, we have limit as x goes to 0 plus of cosine x minus 1 all over sine x plus x cosine x. So when we check the form, what do we have? So we have the limit as x goes to 0 plus of the numerator. So we have cosine x minus 1. So we get cosine of 0 minus 1. Again, cosine 0 is 1. We have 1 minus 1, or 0. And then for the denominator, we have the limit as x goes from the right of 0 of sine x plus x cosine x. So we have sine 0 plus 0 times cosine of 0. So we have 0 plus 0, or again 0. So from these two calculations, our limit is still 0 over 0. So we will again apply L'Hopital's rule. So by L'Hopital's rule, we have the limit as x goes from the right of 0 of the derivative of the numerator. So we have cosine x minus 1 over the derivative of the denominator, which is sine x plus x cosine x. So differentiating, we have the limit as x goes to 0 plus of the derivative of cosine is negative sine x. The derivative of a constant is just 0. So all over the derivative of sine x is cosine x. For the product x cosine x, again we will apply the product rule. So we have the derivative of x times cosine x, or 1 times cosine x plus x times the derivative of cosine x, which is negative sine x. So simplifying this one, what do we get? So simplifying, we have So simplifying, we have the limit as x goes to the right of 0 of negative sine x all over, so cosine x plus cosine x, or 2 cosine x minus x sine x. So evaluating the limit, we have negative sine 0 over 2 cosine 0 minus 0 times sine 0. So this is nothing but 0 over 2 minus 0, or 0 over 2, so we get 0. So the value of the limit that we want is 0. So let's proceed to the second example. So here we want to get the limit as x goes to 0 plus of x ln x. So here we have a product of two functions. So checking the form, we have first the limit as x goes to 0 plus of the first factor, which is x. So obviously this is 0. And then for the second factor, we have the limit as x goes to 0 plus of ln x. So to evaluate this limit, let us recall the graph of y equals ln x. So here we have y equals ln x. So as x goes to the right of 0, saan papunta ngayon ang graph natin? So it goes to negative infinity. So the limit of ln x as x goes to 0 plus is negative infinity. So from these two calculations, this tells us that our limit is of the form 0 times negative infinity. So here we meet the second order indeterminate form. So for this one, our strategy, we have two strategies for this one. So first, observe the following. We can write the limit as x goes to 0 plus of x ln x in two ways. So first, we can rewrite this as the limit as x goes to 0 plus of ln x over 1 over x, or we could also write the expression, so the limit as x goes to 0 plus as x over 1 over ln x. So if we check the form, so what do we have? So for the first conversion, we have the limit as x goes to 0 plus of ln x. So from above, this is negative infinity. And then the limit as x goes to 0 plus of 1 over x is 1 over 0 plus, or positive infinity. So from these two calculations, this conversion allows us to convert 0 times negative infinity to negative infinity over positive infinity. And then for the second one, we have the limit as x goes to 0 plus of x, which is 0. And then for the denominator, we have the limit as x goes to 0 plus of 1 over ln x. So we have 1 over negative infinity, or 0. So from these two calculations, this tells us that the second conversion leads us to 0 over 0. So in practice, again, you have two choices. So you can either convert 0 times infinity to infinity over infinity, or 0 over 0. But as we will see when we do more exercises, one of these two conversions will be easier to handle. So yung pagpili, walang rule, walang general rule on how to do it. I think I would suggest that you just practice, so that you will have a feel of what conversion to use. So here we will use the first conversion. So we have the limit as x goes to 0 plus of x ln x. So we have seen that this is 0 times negative infinity. So this is equal to the limit as x goes to 0 plus of ln x over 1 over x. So this is the first conversion. So the form is negative infinity over positive infinity. So again, this is a limit of indeterminate form type infinity over infinity. So this calls for L'Hopital's rule. So by L'Hopital's rule, we have the limit as x goes to 0 plus of the derivative of ln x over the derivative of 1 over x. So this is nothing but the limit as x goes to 0 plus, so the derivative of ln is 1 over x, And the derivative of 1 over x by the power rule is negative 1 over x squared. So simplifying, we have the limit as x goes to 0 plus of 1 over x times negative x squared. So we have the limit as x goes to 0 plus of negative x, or we have 0. So the value of our limit is 0. Let's start with the third example. So for this one, we need to get the limit as x goes to 0 plus of x to the x. So here we have an exponential expression. So for the form, we have, for the base, we have the limit as x goes to 0 plus of x, which is 0. And then for the exponent, again, we have the same function, so also 0. So from these two calculations, this tells us that our limit is of the form 0 raised to 0. So here is the first of the three exponential indeterminate forms. So for this type of indeterminate form, our general strategy is to use the following fact. So for a function f of x that is positive, then we can rewrite it as follows. So f of x is equal to e to the ln of f of x. So we will use this fact in order to transform our given limit. So we have rewriting, so we have the limit as x goes to 0 plus of x to the x. So we have seen that this is 0 raised to 0. So by the fact, so this is the limit as x goes to 0 plus. So here we, from the fact, we take f of x equals x to the x. So we need to verify that this function is positive. Well, since we are getting the limit as x goes to 0 plus, we are getting values that are positive. So x to the x is always positive. So using the fact, we can rewrite this as e to the ln of f of x, or e to the ln of x to the x. Then from there, we will use some properties of the natural logarithm. So we have the limit as x goes to 0 plus. So for the natural logarithm, yung mga exponents na nasa loob ng ln pwedeng lumabas, no? So we have x ln x. Tama? And then from there, we will use the continuity of the exponential function. So by the continuity, yung limit aakyat sa exponent. So we have e to the limit as x goes to 0 plus of x ln x. So this limit we have seen in example 2, and its form is 0 times negative infinity. And by example 2, we have seen that its value is 0. So we have e to the 0, or 1. So the value of our limit is 1. So here we can see that for exponential types, from 0 raised to 0, dadaan ka papuntang 0 times infinity, and then for this one, you can convert it to either 0 over 0 or infinity over infinity. So sa lahat ng exponential types, so kahit pwede rin to sa infinity raised to 0 or 1 raised to infinity, we will use the fact para ma-convert siya sa 0 times infinity, and then from 0 times infinity, we will finally convert it to 0 over 0 or infinity over infinity. So that is our general strategy for the three exponential indeterminate forms. So let's proceed to the last example. So here we have example 4. So we get the limit as x goes to 0 plus of 1 plus x raised to the cotangent of x. So again, this expression is exponential. So to get the form, to check the form, we get the limit as x goes to 0 plus, so the base is 1 plus x, so this is 1 plus 0 or 1. And then for the exponent, we have the limit as x goes to 0 plus of cotangent x. So to evaluate this limit, let us recall the graph of cotangent x. So paano ba? So ganyan yung itsura niya, no? So what can we see now? So as x goes to the right of 0, saan papunta yung cotangent x? So it goes to the graph of cotangent x. So this is y equals cotangent x. So the graph goes to positive infinity. So here, using these two calculations, we see that our limit is of the form 1 raised to positive infinity, or 1 raised to infinity. So here we encounter the third exponential indeterminate form. So again, our strategy is the same. So from 1 raised to infinity, dadaan tayo sa 0 times infinity, saka tayo pupunta sa 0 over 0 or infinity over infinity. So for this one, again, we will use the fact. So we can rewrite this as the limit as x goes to 0 plus of e to the ln of 1 plus x raised to cotangent x. So here, for the condition that f of x equals 1 plus x raised to cotangent x is positive, is easier to see, no? Because cotangent x as x goes to the right of 0 is always above the x-axis, so its value is always positive, and 1 plus x is always greater than 1, so meaning it's greater than it is always positive, so we don't have any problem there. So we have the limit as x goes to 0 plus. Again, we can put down the exponent, so we have e to the cotangent x ln of 1 plus x. Again, by the continuity of the exponential, pwedeng umakyat ang limit. So we have e to the limit as x goes to 0 plus of cotangent x times ln of 1 plus x. So before, so we have reached the part where we need to evaluate the limit on the exponent. So let us first consider that limit before we evaluate this one. So for the limit on the exponent, we have the limit as x goes to 0 plus of cotangent x ln of 1 plus x. So checking the form, we have the limit as x goes to 0 plus of cotangent x. Again, we have seen from above that this is positive infinity, and then the limit as x goes to 0 plus of ln of 1 plus x is nothing but ln of 1 plus 0 or ln 1, so this is 0. So from these two calculations, the limit on the exponent has the form positive infinity times 0. So we have an indeterminate form, 0 times infinity. So we have two choices again, no? So we can convert it to either 0 over 0 or infinity over infinity. So for this one, I will convert it to 0 over 0. So we have the limit as x goes to 0 plus. So yung 0 dito ay yung ln 1 plus x, no? So we will just retain it as is, and then we will divide this by the reciprocal of cotangent x. So now, when we check the form of this limit, this is now 0 over 0. Before we apply L'Hopital's rule, let us try to simplify first the expression para mas madali mag-derivative. So here, what is the reciprocal of cotangent x? So by definition, it is tangent x. And then again, this is still 0 over 0. So we can apply L'Hopital's rule. So we have the limit as x goes to 0 plus of the derivative of ln of 1 plus x over the derivative of tangent x. So what is this one? So we have the limit as x goes to 0 plus of 1 over 1 plus x, and then the derivative of 1 plus x is just 1 by the chain rule. For the denominator, the derivative of secant of tangent x is secant squared x. So evaluating this limit, we have 1 over 1 plus 0 over secant squared of 0. So we have 1 over 1 squared, or 1. So the limit on the exponent here, so let's go back. So the limit on the exponent is 1. So we have e to the 1, or e. So the value of the original limit is e. So don't forget, after calculating the value of the limit on the exponent, put it back on the original calculation. So that's it for L'Hopital's rule. So we end the lecture with the following exercises. So please try to answer them. So first, we have the limit as x goes to 0 of 1 minus cosine x over 2 to the x minus 3 to the x. So for this one, you might want to revisit the derivative of a to the x. Next, we have the limit as x goes to pi over 2 from the right of tangent x over ln of 2x minus pi. So for this one, to check the form, you might want to revisit the graphs of tangent x and ln x. So next, we have the limit as x goes to 1 of 1 over ln x minus 1 over x minus 1. So for this exercise, you might need to apply L'Hopital's rule more than once. Next, we have the limit as x goes to positive infinity of x cubed times e to the minus 2x. So again, here you might need to apply L'Hopital's rule more than once. And then lastly, we have the limit as x goes to positive infinity of 1 minus 2 over x raised to x. So that ends the lecture for L'Hopital's rule.